Hello. In this video, we will discuss about power functions. Last time when we introduced polynomial functions, we saw that polynomial functions are actually sum of power functions. So understanding of power functions will help us to understand polynomial functions better. The idea for this graph, this lecture is to understand power functions from the perspective of sketching a good polynomial function. Okay. Power function in general can be written as a x to the power of n, where a is a constant, any real number, and n are natural numbers, 1, 2, 3, 4, like that. Basic power functions will be like linear function, quadratic function, cubic function, where n is 1 is linear. Let me take and show you what these functions are. So let's say Lx is a linear function equals to x, and qx is a quadratic function which is equals to x squared, and let's say cx is equals to x cubed. Now Lx is just a line, and you know drawing a line is like this. So in a coordinate system, it goes through origin and it is always rising. And there is an intercept, and the intercept is at origin. In quadratic function, also you'll find that the intercept is at origin, but the line or the graph of quadratic function doesn't cross the x-axis. It actually turns, right? And in case of a cubic function, the graph crosses, but in a slightly different way. See how it bends. Do you see how it bends? Like this, and then crosses. This is kind of a bend. Here the concavity changes. Concave down and then concave up, but it crosses. So what you noticed here is that for a linear function, how does the x-intercept look like? X-intercept is crossed, line is crossed, but in quadratic function it turns, and in cubic it crosses but with a bend. Okay, now let's try to understand why this difference. You can see that in x, Lx equals to x is linear, but if we say qx is x squared, you think like this. X squared is like x times x, so that means 2 times, it's like 2 x's, and here x cube is x times x times x. There are 3 x's involved. How do they make things different? This is what we have to understand. Well, one thing is there, that if we check a value at 0, what is L0? L0 is at when x is 0, we get 0. How about Q0? Q0 is also 0. And how about C0? C0 is also equal to 0. These are called zeros. These are our zeros, right? Why zeros? Zeros because at a value of some value of x, the output is 0. We are calling them zeros. And earlier I was talking about x-intercepts. Now these points where our graph touches x-axis is also a 0. Why is it a 0? Because the value of the function is 0. Okay. So these are also x-intercepts and they are also zeros. But two things which may point to the same point. In this case, in all the 3 cases, that is origin. But two things are very different. How are they different? Difference in 2 things have been highlighted because of multiplicity. See how many zeros are here? If you look at this equation, x is 0, so the function is 0. So there is 1 0, right? How many zeros are here? X squared actually is to the power of 2. So x times x, we call them 2 zeros. How about this? There are 3 zeros, right? Cube. So 3 zeros. This is called multiplicity of 0. So basically what we see here is x-intercepts don't have any multiplicity. These are just the points where the graph touches or crosses the x-axis. But zeros are similar to x-intercepts since they are the same points. But zeros also decides the behavior of the graph at that point. The behavior is very different, you have seen, right? Here it goes straight, here it turns, and here it kinds of bends and then goes. This kind of thing we call point of inflection. You'll see in calculus and other courses here where the concavity changes. Okay, so today in this, by now we have learned difference between x-intercept and zeros and how multiplicity of zeros modify the way graph interacts and the way the graph should be sketched at x-intercept. Okay, now let's look into further details of our quadratic and cubic function. Okay, so let's go back to this quadratic function. Qx equals to x squared and Cx equals to C of x equals to x cubed. And let's take a broader view of these. Okay, let me draw this first for you. So I'll draw both quadratic and cubic function here. Now, well, if x is 0, x squared is 0, so we get this point. Now if x is 1, 1 squared is 1, so we get another point. If x is 2, 2 squared is 4. So let's say this is 1 and this is 2, so add 2, 1, 2, 3, 4, we get this point. Okay. Now if x is half, then x squared is 1 over 4. So at x equals to half, let's say this is our 1 over 4 point. Similarly, on this side, if x is minus half, then we get this point. If x is 1 minus 1, then minus 1 square is 1. So we get point which is at the height of 1. This is 1 for us. Okay. And when x is 2, 2 square is 4. So we get a point which is kind of here, right? This. And let's join these points. Okay, now what you noticed as we talked earlier, the graph bends, right? It turns at this point at origin. Second, what also you notice is that for minus 1, this is minus 1, right? And this is plus 1, we have the same value. So if I join this point, we'll see this distance is same, correct? Add 2. And at minus 2, the function has same value. The value is 4. So then that means they are 2 away, right? They are 2 away. So for the same value of y, for plus 2 and minus 2. So what we notice here is that f of minus 2 is equals to f of 2. Is it okay? Similarly, f of minus 1 is equals to f of 1. In general, you will see that f of minus x is equal to f of x. So that means for let's say if you put x as minus 10, square will be 100. If you put plus 10, square will be 100. So the output is going to be same. Okay, I should have written q here because we are defining this function as q. Okay, but I have just wrote, sorry for that. So we think it is like for this function q. Okay, this kind of symmetry which you see, it is symmetric about a line, correct? So it is symmetric about a line. And which is this line? The equation of this line is x equals to 0. It is a y-axis. Is it okay? So it is symmetric about line, and this kind of symmetry is called even symmetry. So a function with even degree, a power function with even degree will show us even symmetry. Now we will see Will all functions with even degree show this? All these characteristics? Let's check it out. Let's try another function. Let's say dx equals to x to the power of 4. Okay. So instead of 2, we are doing dx equals to x to the power of 4. Let's try to plot this particular function dx x to the power of 4. When x is 0, what do you get? 0, 0. This is our point 0, 0, which is same. When x is 1, 1 to the power of 1 is 1. So same, correct? 1. It does have that even symmetry, correct? But if x is 2, then 2 to the power of 4 is 2 times 2 times 2 times 2, 16. Wow. So that 2 is not going to end here at 4. It is going to go way up. Okay. Similarly, if it is minus 2, that is not going to end here. At minus 2, the value is going to be plus 16. In a way, what we are trying to say is this will be much steeper. How about when the x value is half or minus half? In both the cases, 1 over 16. So this will come very, very close to our x-axis. So if we have to draw x to the power of 4, then how will that look like? I think something like this. This becomes so flat. Do you see that? But it will, ones are common, right? And then kind of steep here. Do you see that? So very, very steep, increasing very fast, and here becoming flatter and flatter and closer to our x-axis. Correct? But well, the even symmetry is maintained. As we saw, all the values are equidistant from y-axis. Right? So f of minus x, in this case d of minus x, will be equal to d of plus x. So whether it's to the power of 4 or 6 or 8, same similar characteristics will be shown. All will go through the point origin 0, 0, 1, 1, minus 1, minus 1. Between 0 and minus 1, the graph will become closer and closer to x-axis as the degree, even degree, is increased. And it will be steeper and steeper as the degree increases. Now let's see what happens for our cubic function. Okay, cubic function will look like kind of like this. Let me first draw the cubic function, and then we'll put the points on it. Okay, x cubed. When x is 0, 0 to the power of 0 is 0, 3, 0 to the power of 3 is 0. Okay, now if x is 1, let's say this is our 1, this is our 1. Okay, similarly here 1 and 1. Okay. When x is 2, then 2 cube is 8. It will be here. So at 1 we get 1. At minus 1 we get minus 1. So this point is minus 1, minus 1. Okay. But this point is 1, 1. At 2, somewhere here, it will be somewhere here, which will be minus 2, minus 8. But here at 2, we got 2 and 8. Correct? Now, you see, this does not have even symmetry, but it has another kind of symmetry. The symmetry here is, if you see from this point, origin, this distance and this distance are same. Similarly, if you check these points with origin, okay, then this distance and this distance is same. So we call this as a point symmetry. So they have point symmetry. And these functions are also called odd functions. Odd in this, f of minus x is equal to, is it equal to fx? No, it is minus of fx. And that's why it's called f of minus x. That means f of minus 1 is minus 1, not plus 1. Minus of fx. Do you see that? So that is how the function with odd degree look like. Now, what will happen if I change this to, let's say, ex, where the power is not 3, but 5 this time. So when the power is more, then 2 to the power of 5 will be a much higher number. So it will be steeper, correct? Similarly, if I take a point half here, right, in between 0 and 1, then 1 over 2 to the power of 5 will be definitely far more than 1 over 8, correct? So that will come closer and closer to x-axis. Do you see that? So here the graph flattens out just as we saw previously. 1 and 1 values will be maintained, right? And then it will become much and much steeper, like this. Do you see that? So in both the cases, we see that the graphs become much steeper. Invariant points which don't vary are the points for x values of -1, 0 and 1. X square and x to the power of 4 and such even degree power functions will show us even symmetry, and the odd degree power functions show us point symmetry, which we call also as odd functions. Okay. Now, one more thing which I would like to reflect here, and that is in case we took coefficient of x square as positive, right? Now, if I change that coefficient of x square to positive instead of 1, -1, then what will happen? These graphs will flip, right? So they will be in this direction, okay? And this will flip. This will be in this direction, right? So it will just change the direction because it has to reflect on x-axis. Is it okay? Now, one more thing which I would like to point out here is for even function, you also observe that both sides face same way. Here they face opposite way. Now, coming back to polynomials. Polynomials, as we defined earlier, is equals to an x to the power of n plus an minus 1 x to the power of n minus 1 plus so on a2x square plus a1x plus a0, correct? Now let's look into end behavior. All this exercise, why are we doing all this? Just to understand the end behavior. Is it okay? What is end behavior? What happens when x approaches positive infinity, or what happens when x approaches negative infinity? That's end behavior. When we say x approaches positive infinity, that means this positive infinity, right? Very large positive value. Approaches negative, very large negative, right? So let's just see both end behaviors for even and odd function, okay? This is even degree, okay? And this is odd degree, right? So for even degree, what is happening? This is our even degree function, right? For even degree function, when x approaches positive infinity, y or the fx or qx also approaches positive infinity, correct? In both the cases, both the sides face same direction. Do you see? Even functions face like this, correct? And for odd, what is happening for odd? We see this is positive side, y does approach positive infinity, but when x is approaching negative infinity, y approaches negative infinity. So basically the function actually is like opposite sides. Do you see that? This is all when a is positive. When a is positive, that means when a is greater than 0, correct? Now if a becomes less than 0, then what happens? If a is less than 0, that means, let me write you, when a is less than 0, how will my equation look like? Then in that case, I'll write y now in this case, minus x square. This is what when I say a is negative, okay? And in this case, y is minus x cube. Do you see that? A is negative. In that case, what happens? In that case, my graph is going to flip. Instead of going from here to here, this part gets reflected here, that gets reflected here, minus, right? Reflection on x-axis, correct? So the graph actually goes like this. And for this function, it will face downwards. Do you see? So the end behavior will reverse. Correct? What happens when x approaches positive infinity? For this, y approaches negative infinity. When x approaches negative infinity, that means going this side, y is again approaching negative infinity, not positive. So this is dominated where positive or negative side of y is a value. Do you understand? And what does n decides? If n is even, both face same side. If n is odd, they face opposite sides. Is it okay? When x approaches positive infinity, y approaches negative infinity. But when x approaches negative infinity, y approaches positive infinity, opposite sides. Well, this may look very complicated, but one rule helps us to bring us out. If a is positive, then in our first case we saw, then right side is up. So we'll write here big and bold, if a is positive, then right side up. What I'm trying to say is, did you see our initial graphs? A is positive, right? Look here. A is positive, right? One. Right side up. Do you see right side up? Now second, if n is even, then what? If n is even, then both same side. And if n is odd, then opposite sides. You get it? So, by understanding our polynomial functions, we can conclude that if the degree of our power function is even, then the end behavior both face same side. It could be down or it could be up, right? If a is positive, then right side is always up. Correct? So this is what we got out of it. And now let me take an example and check with you if you have really understood. Okay? So I'll take another sheet of paper and then we'll work on that. Okay? Power functions, and I'll give you one equation to try it out, and then we'll see how close you are. We'll make a very, very rough sketch, right? And let me write a polynomial function here, and my polynomial function is y equals to minus 3x to the power of 7 plus 2x to the power of 5 minus something. Let's say 4x cubed plus 3. Let's say this is my equation. Now, what is the leading factor here? Leading term? Leading term is this. Correct? Is the degree even or odd? The degree is odd. So n is odd. And how about a? A is negative. So what is the end behavior? Can you tell me the end behavior of this? Negative means both functions should face this side, right? Right side is down, not up. And odd means opposite behavior. Do you see that? So that's my end behavior for this function. Do you get it? Now another example. Let's say if I have equation y equals to minus 2x, x plus 4, 3, x minus 3, 2, and let's say x plus 5, 7. Okay. Now, what is the degree of this polynomial? The degree of this polynomial is 7 plus 2, 9, plus 3, 12, plus 1, 13. So n is 13, is odd, right? And again, negative coefficient, so this will also behave like this. But if I make this square, in that case, what becomes the degree of this function? N becomes 7 plus 2, 9, plus 3, 12, plus 2, 14, right? Now it becomes even. Even function with a value negative, how will that look like? So I'll draw this end behavior on the same graph, okay? So it will be something like this. Both sides same. Do you see? Because even and odd. Correct? Let me take one more example just to give you one with a positive leading coefficient, okay? Y equals to 4x to the power of 7 minus 3x cube plus 9x to the power of 8 plus 5. Now, which is the leading term in this case? Well, I've mixed them up and the leading term is not the first term, right? You have to be careful. Check it out. 9x to the power of 8 is our leading term. So, what is the degree of this function? N is 8. Degree is even. Is it okay? How about A? Is it positive or negative? A is positive. 9. So, it's positive. Is it okay? So, how will this function look like? Let me draw this function in green color. Okay. Okay. Now, since it is even, so both will face the same side and A is positive, right side up. So here, right side up. Is it okay? And even, both face same side. So the end behavior of this function is kind of like this, okay? Now let's go back. This is negative and odd. So in this case, negative and odd, we found it was like the right side down because negative, odd, opposite. Do you understand? Now, I'm talking about this blue one here, right? Just to summarize, N is even, but A is negative, right? A is negative. So negative means down and even means same side. So this is how we will finalize the end behavior of a polynomial, right? So this end behavior of a polynomial we'll see how to use this end behavior to sketch our polynomials in the next lecture, okay? Thank you.